Here's a related rates question to do with volume and surface area of a cube. A cube is expanding, so its volume increases at a constant rate of 10 centimeters per second. Find the rate of change in its total surface area at the instant when the sides are 20 centimeters long. So I like this volume increases at a constant rate of 10 centimeters cubed per second. So that's telling us that dV by dt, the rate of change of volume with respect to time, is 10. I won't put the units in, but that's something we're going to use, and it doesn't change, so it's interesting. It's not talking about an instant rate, that is always says it's constant rate, so it's something we can use. Find the rate of change in surface area at the instant when its sides are 20 centimeters. So when you talk about the instant, firstly, that makes you think we're talking about relative rates, and secondly, this 20 is not going to be substituted until the end. So we know that if we talk about an instant, we don't use that until later. So there's certainly the sides, we can't build a model around sides being 20 centimeter long. That's just a value we can use at the end. Now, also, this is about volume changing with time and surface area changing with time. And you can see, so if we call surface area A, so we're going to look for like dA by dt. And you can see if you've got a cube and your side lengths are changing, then your surface area is going to be changing and the volume is going to be changing if the cube is changing size with time. And those rates are clearly going to be related in some way. So if we don't know the side lengths, but we know that they're changing, they must be changing to change the surface area and volume, we're going to call them x. So x and x and x. So we probably want to find, with a question like this, probably just write down anything. If you don't know how to get started, just write down whatever you potentially know. So we know that V equals x cubed. That's a good start. Volume of a cube is x cubed. Then you could potentially differentiate that with respect to time. So dV by dt is going to be, so it's 3x squared dx by dt. Okay, that could actually be quite useful if you think about it, because out of these terms we could find when the side length is 20, you can use this 20 here, and you know that dV by dt is constant, so that would actually tell you the rate of change of the side lengths at that point, which probably will be useful for later. But let's come back for a minute and get an expression for surface area, which we're going to call A, as in surface area. So A for a cube is 6x squared. Surface area is 6x squared. We're going to want to differentiate with respect to time, as we always will for a related rates question, dA by dt, which is what we actually want. So find the rate of change in its surface area. So we're looking for dA by dt equals, we'll differentiate the 6x squared with respect to t, so differentiate with respect to x, and then you're going to need a dx by dt. It's that chain rule arrangement in implicit differentiation. So it equals 12x dx by dt. So now, if you look at this is what we want to find at the moment when x equals 20. So when x equals 20, well, we know we've got 12 times 20. But this is what we want to find at the end, and we're going to need this, but we can get dx by dt by using this constant dV by dt. So if we can find dx by dt from this equation, we can substitute it into here. And so when x equals 20, when x equals dV by dt equals 10 centimeters per second minus 1, 10 centimeters cubed per second minus 1, and that's a constant rate. So if we substitute into this equation, call it equation 1, we we know that 10 equals 3x squared, well x is 20 squared times dx by dt. So, well, 20 squared is 400. 400 times 3 is 1200, so dx by dt equals 10 over 1200, which is 1 over 120. Over 120, and I suppose that's centimetres per second. So that's the rate of change of the side lengths. So if we call this equation 2, so the dA by dt, so equation 2, dA by dt, remember we're only interested at the instant when x equals 20, equals 12x, so 12 times 20, times dx by dt, which is 1 over 120. So that's not too bad, you know, because you can, if the 20 and the 120, you can call that 1 over 6. So 20 divided by 120 is 1 over 6. And then you've actually just got 12 over 6, which is 2, equals 2. It's the rate of change of surface area with respect to time, so that must be centimetres squared per second. So the surface area is increasing by 2 centimetres squared per second when at the instant when the side length is 20 centimetres.